So let's start. So, oh, does that capture the OBS thing? No, it's recording. Okay. It both reloaded the page and started recording. Right. So first, an advertisement. So there's a nice talk. Well, nice. I don't know. I haven't seen it yet, but I presume I show around this afternoon. So it's in Edinburgh, but I've posted on Teams the Zoom link and the password. They're not made public for obvious reasons, about the cognitive and human factors of formal methods. So here we're saying a lot of the technical aspects, but then what are the barriers to adoption? I mean, you've experienced some of them with the quality of the tooling and so on, but Shriram has actually done the work of figuring out some of these things. So I think it will be interesting. It's at 4 p.m. If you want to attend the talk, you can just go find the link on Teams. By request, there will also be another lab next week, another additional lab next week on Tuesday at noon, just like today. So if you want to come, you're more than welcome to. This will be the last lab before the submission deadline. So do with that what you want. Also, yeah, yesterday I was a bit frustrated by the fact that Otto was not able to figure that out, and it was indeed a bug. I was planning to try to fix it, but turns out it had already been fixed in the development version. So this is easy. So of course it should be found automatically. I don't know what the problem was. I didn't track it down. So if you want to try to upgrade to the development version, Auto might be stronger, but I don't know whether it will be compatible with everything in the coursework. I haven't tested.
Classic.
So
there's nothing like the Agda development team for moving fast and breaking things.
Yeah, so I have tried to make sure that the coursework was tied to a specific version of everything, and with all of the constraints clarified so that you wouldn't have any surprises. So if you decide to move away from that target, you're on your own, I'm afraid. Okay. Yeah, so that was the ads thing, yes. Right, so yesterday we stopped at parity, and we're saying, well, it's all well and good to be able to decide whether something is even or odd, or even to be given a parity and then decide whether the natural number has that parity. But in practice, there's a more general statement that not only tells you that the number has the given parity, but also computes the parity on the fly. And this way, instead of just saying it's even or not even, you're saying it's even or odd, which is much more useful. I don't think we want to implement this. Or maybe we can.
It's three-liner, right?
Well, yeah, okay.
Okay, no.
It might actually be useful, yeah. Okay.
Yeah.
Right, let's do it. Yeah, so we have only one thing, right, as always. As often, not as always. We only have a natural number, so the thing we can do is split on it. So look at its shape. If it's 0, well, yeah, there we go. That's easy. It's not odd. And we have a proof of that. And otherwise, if we have the successor, what do? Well, we look at the parity of M itself, and we know that we're just going to need to toggle it to negate it, basically. And the proof will hopefully not be too hard. So we use this with construct to say, well, I already know how to decide the parity of M.
Yeah.
That's P. And then I can start inspecting P. Well, it's going to be a terrible name, of course.
Yeah, you basically need to re-implement not on the fly.
Yes. So I'm going to look at what the answer is, and this is the proof. And as we said, we're just going to toggle because it keeps alternating back and forth. So if it was false, now it's true. If it was true, now it's false. And hopefully, yeah, these are just built implicitly. And so now whenever you have a number, you can decide what the parity is. Okay.
One thing worth thinking about is that tells us that every number is at least one of even or odd. But it might be sensible to prove that a number can't be even and odd at the same time.
Yeah, I mean, we could.
So yeah, just
Sure, let's
yeah.
do it.
And that.
We probably don't even need to look at it, right?
Yeah, sure.
If we have,
if you've got even m and odd m, you've got
then bottom
false, and then you.
Whoop. I keep jumping around. So this is the same as saying that even implies not odds, but also if you're just shuffling the arguments around, it's the same as proving that odd is not even, right? So it's a very like 2-for-1 kind of principle. Whoop. And let's do it. So I'm gonna get my arguments. Agda is picking terrible names, but I'm gonna split on both of them anyways. Okay, P and Q maybe.
Right.
So if I get even 0 here, it means the other proof is odd 0, but all the odd constructors are targeting successor of something, therefore it's just the empty type, so we can just dismiss that branch entirely. And then if we have even S of P here, it means that we have an odd of a successor, meaning that we can match on the top constructor, it's going to be odd successor, which means Q is a proof of even, and P is a proof of odds, because we're just switching the parities. Oh, this is actually an interesting little thing. So then we just swap the two proofs around.
There's a couple of subtle little things to say about the way the termination checker is managing this.
Yeah.
But the boring thing to observe is that the invisible number that we're not talking about is getting smaller, so the termination checker sees that and but also we notice that we're making these proofs get smaller, except that we're swapping them over. So they're kind of both getting smaller in sync. And actually, termination checker's happy about that too. It will spot that counts as getting smaller with swapping. Getting smaller in sync with swapping is accepted. So this is fine for 2 reasons, even though it looks a bit weird.
Yeah, so under the hood, the termination checker will try to see when an argument flows back into the same position. And if you're swapping them around, it's going to figure out that after 2 swappings, it flows back into itself. But because every time you're making them strictly smaller, after 2 swappings, you do have something that's strictly smaller. So it's a valid thing. But here, yeah, it's the silent element is the more obvious termination proof. It's always nice when just the indexing is enough to prove something.
Classic, in fact.
Okay, so another thing, maybe we should have some examples, or let's see. We already had some with the equality. I don't know. It's false something.
Do you need parentheses around that thing?
Yeah. Okay. So again, these proofs are really annoying because you're peeling off one constructor at a time, but because we have a function that can compute the proof for us, we don't actually need to write these proofs by hand. Okay. And then this next thing I wanted to discuss, I forgot to start this, is Markov's principle. So far we've seen various decision procedures. So we've seen we can decide equality on natural numbers. We can decide whether a number is even or odd, because every time we're reducing the problem to deciding whether a smaller natural number is even or odd. But sometimes we have decision principles that, or maybe it's not quite a decision principle. It has the flavor of a decision principle. So what's Markov principle? It's telling you that if you have an arbitrary predicate on the natural numbers, and you know that this predicate is decidable, so for all n, I can decide whether P of n holds. And additionally, so there are various ways to state this, but you could say something like this. It's not the case that the predicate is false for every natural number. And then I don't know if you see where I'm going here, but the idea is that I would like to get my hands on a value of type n, which satisfies the predicate. And it feels like it should be legitimate, right? Because we already know that it's not the case that P of n is false of every single natural number.
That's not the same as knowing exactly where it's true. On the other hand, we have a strategy which is at least plausible for figuring out where it's true, namely try 0. If that doesn't work, try 1. Keep going. This not for all not is supposed to be at least some clue that we couldn't possibly go on forever, even if we have no idea how long it'll take. So yeah, this is, but it's somehow a sort of unbounded form of computation. So it's extra. It's not all the way to kind of something classical logic or anything like that, but it certainly doesn't fit in with the regular box.
So I mean, we can write something like this. If we have a loop that starts with whatever given, I need to introduce the predicate. The idea is, as Gunnar was saying, for every time I'm going to try my candidate and hopefully it works. So I can try to see whether P is true at I. And if it yes, if it is true, and no, not PI. If it is true, then I'm happy. I can already conclude. I found my witness. It's I. And then if it's not true, well, I can just go.
Yeah, and termination checker doesn't like it.
Some more.
Also, you'll notice that we've made no material use of the fact that it can't go on forever.
Yeah, we have this statement here, but we never, I mean, we can't really look into it because it's a negation. So just purely negative information. But this should be a legitimate, this could be a legitimate principle. So the point is that the termination is necessarily restricted. I mean, as you know, you can't always decide whether a function is terminating. And so it's going to restrict you in what you can do, or even what you can prove terminating. So here, it's not even that it's not seen as terminating. It's like there's no way from inside ACDA itself to prove that such a function would eventually terminate and return a value. So whenever you're defining a type theory, there's always some limitation as to what you can prove. And you may want to think about like the principles, the reasoning principles you would like to add as an extra thing. So I mean, the typical examples that we have are all of the uses of the FFI purely for programming purposes, but sometimes it's also like these logical principles.
That's
So,
foreign function interface, if you were
oh yeah, sorry.
wondering.
And ooh, oh, I don't think we need to say a name. So there are escape hatches. So if you're really sure that you're doing the right thing, you can declare that something is terminating. Or if you want to be a bit more careful, you can say it's non-terminating to avoid things blowing up in your face, because I think this could blow up in your face, right? The proof here could
Yes. Oh, absolutely.
be invalid.
Yes. So you're in the situation where we don't just do computation on closed values. We do computation in the presence of free variables. So in the presence of some hypotheses. And the thing that's always frightening is that in the presence of hypotheses, all the lies are potentially true. Someone could tell you they have a proof that we don't go on forever, and they could just be lying their head off, and we might fall for it and get into a flat spin, right? The thing that's bad about this is that we've got no way of calling out anyone who tries to use this to bamboozle us, even if it makes some sort of sense.
So just to give you an example, so I can say that I can find a number that is odds by using the Markov principle. Of course, it's a bit silly because we can all find a number that is odds, but I need to prove that it's not the case that for all n it's not true that n is odds. And I think I can do that with node of, say, 11.
What? Their case now.
Mm. There can be.
Uh-huh.
Hmm. What? Oh. Oh yeah, of course. Okay. Okay, that was maybe not the best example. Yeah, so I'm not dismissing the thing because it's impossible. I'm proving that if I I'm just confusing myself now. Right, this gives me a function, like this gives me a proof of the negation of odd 11, and to use it, I'm calling it with a proof that odd 11. Okay, that's fine. Sure, whatever. But now if I normalize this thing, which I cannot do, of course, because I didn't give it a name, so there we go. And odds. What do you think the value will be? I could make it a natural number, actually. Oop. Yep. Because if you look at Markov, right, we're entering it at 0, and then we're checking in turn for every natural number. So the fact that I selected 11 and passed 11 in the proof has no influence whatsoever on the value that this process is going to find. It's always going to find the smallest one. So if I evaluate it, I will hopefully get 1. There we go. But then the other thing, danger, is something like this. Which one should I say? Exists. and then such that n times 0 equals 1. Okay, let me import something. Net base using star. So the idea is that when you're in an absurd context, you can prove anything you want, right? So here I have my proof of the empty type, which is absurd, but there we go. And then using Markov principle, so case off here is just a way to pass an argument to a function. So I'm saying I'm going to look at this empty thing and I don't need to define anything. It's the principle of explosion that we saw earlier. And here I just need to be able to prove that for any natural number, I can decide whether n times 0 is equal to 1. And this is easy to do because we had nat ec dec on hand. So we can always test something like this. And if I try to normalize danger, ooh. Is Agda clever enough to?
Surely not.
It's not stuck though. Oh, it's busy. Okay. Okay. Is it still busy? Yeah, it's still busy.
How busy is it?
It doesn't seem very busy. I don't know. OBS is more
Yeah.
of a problem. Anyways, but the idea, right, is, as Connor was saying, we're normalizing open terms. So this is just a lambda abstraction. And when you're normalizing a lambda, what you're doing is you're saying, well, I'm binding the first variable, and then I'm normalizing the body of the function. And then here you have Markov. I mean, I guess it's not too bad because it's a tight loop. It's not allocating too much and so on, right? So the loop is going to look for a number such that n times 0 equals 1. Oh no, I made it non-terminating, so it's not.
Yeah.
So, but why was it reducing in the odd example then?
I don't know.
That's very strange. I don't know what the heck is going on. But because you're in an absurd context, you're able to prove that allegedly it's not the case that for n, n times 0 is different from 1. And so then it went on its merry way to try to find such a witness, which is why, I mean, you may want to add more reasoning principle, but you have to be careful about the way they're implemented. And in this case, it wouldn't be safe to just let it reduce all the time, because the compiler could just hang by trying to convert, let's say, a vector of size something where, and a vector of size
whatever that number is.
Whatever that number is, and a vector of size 3. And you'd be like, well, I need to check whether it is, whether it reduces to 3 or not. Okay. Oof, yes. Right, so we've seen some decision principles, but every time in the examples, I've been very careful to only ever write this kind of statements where you're not quite getting your hands on the proof of parity. You're just getting the result of running the decision procedure. Here it's the same. You are getting the proof that you got yes. But sometimes you just want the proof. You don't want a value of type decidability of even n or odd n, etc. And so it turns out that using the sort of type level computation magic that we're doing here to find a witness, you can similarly run these decision procedures at the type level so that you can statically extract the values, so that you don't need to write this kind of stuff anymore, for instance. So what's the idea? Well, the idea is that you're going to write a function which, as an argument, takes a constraint that the decision procedure has been successful on that input. And then if it has been successful, Agda will be able to produce that argument automatically. If it has not, it will just complain to you that that constraint is, cannot be satisfied. So the idea is to define by large elimination from any decision procedure whatsoever into sets what it means for the decision to return yes. And of course, you do this by pattern matching. And if you have yes of something, it doesn't matter what the proof is, then you're going to return something that's trivially true, because it is the case that yes is yes. So I hope I have it in scope. Yeah, I do. And then if you're asking whether no is yes, well, you have something that's trivially untrue.
Right. So Guillaume used the phrase large elimination. What that means is that we're computing a type as opposed to computing a value that has an ordinary type. So yeah, so set is a type of types. It lives one level further up than your ordinary types does. But that's fine, you know, you're allowed to compute stuff. If you've got data in your hand, you can compute anything you like with it. Yes.
And then we have this magic function here, which is really helpful. Oh. Well, I guess I could have removed the definition too. So what is it saying? It's saying that if you can decide whether A is inhabited, and this decision is called D, and then additionally you know for a fact that D is yes, then you get to extract an A. And how do you do this? Well, you run the decision and you observe that it is indeed a yes, and then you got your hands on the proof. So it's magic because it feels a bit silly, but that's the way it goes. And I left this one out, but we can write it if we want. So if instead the D had evaluated to no, then this implicit proof here would have type empty. And so by matching on it, we can just dismiss the branch. And this is so obvious because we're not popping any constructor or anything. It's immediately the empty type that Agda is clever enough to see that we don't even need to explain it. And so we have this. Why is this a different one? I shouldn't do is even anyways. I should do is odds. Is odds. Oh, I know why. Yeah, okay. Is yes. Odds and odd n. And is odd is magic is no odds n. Oop. I need to pass the proof explicitly. Okay.
That's the way.
And now if I move this just above here, instead of having this pile of crap here, I can just say is odds 11. And it works.
Yeah. We need to see what happens when you try and fool it.
Oh, yeah. yeah. I'm always on
Let's see what happens if you try and just use this magic device to get a proof that 12 is odd. Or that 11 is even.
Oh, even.
Yes. Right. You're saying, oh, there's a hidden thing of type false that I just can't figure out, but maybe you could help.
And of course, you try to supply it. So sometimes yellow is fine. It's a problem you can solve. But so some of you I know ask me, like, if there is still some yellow in the file, is it a problem in the coursework and so on? It depends. If the yellow is a proof of false, yes, it's a problem. If it's something else that's a bit unfortunate,
yeah, generally it means you haven't given enough information to convince the type checker everything's fine. That's without prejudice as to whether or not this information exists. Right. Here it does not.
Yes. So let me comment this up also. Maybe can move this around here. Okay. All right. So now we've seen decidability. Well, we've seen various proofs. So first, we only saw proofs of equality, which were convenient, but sometimes you want to talk about something else than just two things being the same, like whether they're even or odd. So then we saw that. We saw decidability for these various things. But of course, these are only, they're atomic in a sense, right? You're talking about a very specific type and like a very specific kind of predicate or relation on that type. But if you want to build a library and be able to reason in a compositional manner about the problems you're facing, then you need other kind of predicates. And in particular, here we're going to look at two predicate transformers that are taking an arbitrary predicate over, say, natural number, and is going to be able to lift it over, say, a list of natural numbers. But you don't want to be doing it for every single predicate. You don't want to have the predicate saying all of the numbers in my list are even, and then you'll have another one for all of the numbers in my list are odds, all of the numbers in my list are equal to 3, etc., etc. Instead, you can abstract over this idea that all of the not even all of the number, all of the values in a given list abide by some predicate. So let's do all first. So all, because it's going to talk about arbitrary values in a list, it's going to be generic over a type A. And then it's going to insist that all of the values of type A respect a given predicate. So we give ourselves a P of type A to set. And then I'm going to put some strategically placed parentheses here to suggest. Oh, I don't have a list in scope. I don't have to have too many things in scope. So. And we actually have some of these in the coursework, these all predicate transformers, although they're slightly different. But the idea here, actually I can remove, do I need to name P? Yeah, I need to name P.
Yeah, you do.
Ugh.
If it's left of the colon.
Because it's uniform, yeah. But if you forget about P here, you can see that we're going from A set to list A set.
It's a wet day, you don't have to jump.
Or maybe, you know what? Rather than pointing at commonalities, we can just, well, it's going to be large, so I should, I can say, what does it mean to have a predicate over a given set, or just a function from that set into set itself? And then I can say this. It goes from pred A to pred list of A. So hopefully this makes it clear that this allows you to build predicates in a compositional manner. So if you have a list of lists, for instance, you can say that, and you want to insist that all of the values deep inside the nesting of lists satisfy a predicate, you can just say all P. And this will lift automatically under the layers instead of having to painfully explain all of the details of everything. And what does it mean for all the values in a given list to respect a predicate? Well, it's going to have exactly the same structure as the list you're talking about. And to insist on that point, we're actually going to use the same names for the constructors. So if your list is empty, it's trivially true that all of the values in it respect P, right? It's Hopefully,
Yeah.
yes. And then if your list is non-empty, I don't know if I gave myself enough variables. X, Y, Z, A, variable Y, Z's, list A. Okay. And when is it true? I'm going to write it like an inference rule. When is it true that all of the, maybe I should write this one like an inference rule also. So this is trivially true. There are no premises. It's an axiom, a leaf in your deduction tree. And it's true that all of the values in x's respect p, if p of x is true, and also all of the values in x's respect p. So I can write it suggestively like this as a reasoning principle. And so now you can build proofs that, for instance, all even 0 to 4 empty lists. And maybe I should write it with the magic thing. E0 2, E0 4. So I'm just copying the structure of the list, and at every point in time, I just need to deal with the one element I am currently considering. Okay? And so I lied a little bit when I said that it was about predicate transformers. As you saw, a predicate is defined as a family indexed by A. And so in practice, it means that it doesn't have to be just proofs that you're storing in these things. You can store arbitrary data that is indexed in an interesting manner by this thing of type A. And so you can actually use this to describe some kind of data structure with interesting indices. So for
Like
instance,
a spreadsheet.
Okay. Is this a spreadsheet?
Well, no, you can have two layers of, if you've got two lists, right?
Yeah, okay.
A list of row headers and a list of column headers.
Okay.
And you have some kind of cell type that's indexed over a row and column. Then
Okay.
you can build a rectangular matrix of things where the cell is doing the right thing.
Do you want to do it?
I'll do it. I'll do it. Right. So actually, I want to call this thing spreadsheet. And it says if I've got two types, row and column, and I've got a thing called cell. So maybe the rows are the students in the class, and the columns are the marks in the assignment, and this is a mark return. So I've got something where I know how to give a type to the individual cell based on what its row header is and what its column header is. Then I'm going to give a type which has a list of row headers and a list of column headers and gives me rectangular data. So a spreadsheet, maybe I should make R and C hidden, because hopefully we can figure that out from cell. Okay, so spreadsheet cell R's C's, rows, columns, is what? What happened there? Oh, that's, let me just, fingers. I'll just delete that.
Yep.
Right. So, what am I going to say? I'm going to say that I need something for all the rows. Don't know what it is yet.
So it's rows first.
Yeah.
Matrix.
Okay. And then I get a lambda R telling me the header of the row I'm now talking about. I'm trying to figure out something that's going to work for all the rows, and I get to know. So this is telling me, yeah, ours is my list of students, and little r is a hypothetical student. Okay, and now I say, I want something for all the columns. And then just by way of not thinking, I'm going to say, well, give me a typical column header. And now I say, okay, I would now like to be given a cell for this student and this assignment. Reasonable? So I don't know what, whether we can think of a quick example of this.
So I think, oh no, it's per coursework. Well, if it were per classes, right? This type of cell could be trivial if the student is not enrolled in that class, but interesting if they are enrolled.
Yeah, I mean,
with
other
some
more
structure, right?
boring and prosaic things involve, like for each assignment, we might be recording the maximum number of available marks, which might differ from assignment to assignment. And then we would want to make sure that the entry in each cell was in the appropriate range for that assignment. And that would certainly vary with the column.
But hopefully not with the row.
Yes. Some students are not allowed to score as many marks. So, yes. No, so that's the sort of structure. And then you can see these things are bound to be rectangular because the length of the all is the same as the length of the list. And we're using the same column headers for each row. So we're going to get something rectangular. So yeah, fun stuff. Also a fun game to play transposition on these things.
Yeah.
We ought to be able to take this rectangular thing and flip it around its diagonal to swap the rows and the columns. It's a good laugh. Just keeping an eye on the actual time, given that clock started late. We do have we're not quite 10 minutes, but 8 minutes of science.
Right, so maybe I can define any, because like I wanted to give an example, but a nice example would require us to make it like level polymorphic, I think, because then we could have a list of sets telling us the sort of elements we're interested in, and then a list of natural numbers. And then you can see that this spreadsheet would give you like cells where at every point, the type is given to you by the row, for instance, and the length of the vector containing values of that type is given by the column. So that would be an interesting instantiation of this. But because the set of set is not set, it's set one, it requires the definition to be a little bit more level polymorphic, which I don't think we'll have time to do.
Yeah, let's do any.
I think instead it's worth having a look at any. And I mean, any is fairly similar, except that now it's not true of all the elements. It's true of at least one element. And then we're going to point to like the element we've picked. It's not necessarily the first one or the last one or whatever. It's just any element that will do. So it will have a fairly similar declaration. So it's again something that turns a predicate on A's into a predicate on lists. Okay. And then, well, do we have any proof of any for the empty lists, for instance? No, there are no elements in it, so there's no chance of an element, any of it, any available elements satisfying the predicate. So we know the list will be non-empty, and then the easy way to formulate it is that the element we're interested in may be at the start, or it may be later in the list. So we typically call these here if the one we're interested in is
You might. I typically call this 0.
well,
But,
yeah,
but
it's the
here is fine.
royal we. I don't
Yes.
know.
Yes.
So if x already satisfies p, we can just stop here and we're happy. Or it might be over there. If it's not here, or maybe it's here, but we don't have a proof of it. We just have a proof that it's somewhere. Oh, I'm just mixing everything up. So we have a proof. We want a proof that it's somewhere in x-axis, and we are going to insist that it's somewhere in x's. Let's draw it like this. Okay?
So you can see these really are a fancy 0 and successor that are guaranteed to give you a number that is in the right range to point to somewhere in the list, and moreover, it points to a position where the where p is actually provable.
Mm-hmm. And so when all gives you like matrices or higher dimensional cubes and so on, you can think of any. Again, it's a predicate transformer, so you can say any of any of any of something. It's more like a path in that space to a cell where something is true. Okay. Do we want to have some example? Any even? Let's use our favorite. Just typing random numbers. All right. I wonder whether yeah, there we go. I don't even need to. Good. Maybe I'll rewrite this one with the magic. So here, auto is greedy, so it was looking for the first one. But if I, after the fact, modify the thing to introduce an earlier even one, it doesn't matter. It's still valid. We're jumping past 2 elements and then deciding to focus on 4, and 4 is indeed even, so we can satisfy the last constraint. And then one question that might be interesting. So we saw Markov principle, right? Where we had a predicate, we knew it was decidable, and we know it was not true that all of the natural numbers were not respecting p. Therefore, we could compute an element of the natural numbers that satisfies p. And we saw that it was not possible to prove it terminating, and it was unsafe to implement, and so on. But for these things, because the domain of discourse has now been shrunk, yeah,
Yes.
to a finite domain, so we're only talking about the values in this list, we can actually explore it in full and prove indeed that if it's not the case that p is not true for all of the element in x's, then there is an element in x's that satisfies p. And so you can write that search function, and I don't think we have time to, but it's a good exercise. So.
It's fun to do. More generally, if you have, if you can show that some test that you're making on elements is decidable, then you can decide it. You can try that test on finitely many things, and you'll get something decidable as well. So it's not just that all and any take predicates to predicates. They take decidable predicates to decidable predicates, which is extremely useful.
Yeah, so this time, I mean, because x's is finite, you can look at it and call yourself on the tail if the first element was not a valid value. You will need to use the proof, though, because at some point, you might allegedly reach the empty list, in which case there will be no more candidates. But because you knew that it was not the case, that all of them were not satisfying, etc., then you can dismiss that branch as impossible. So we're seeing both that here we have something that gets smaller, which justifies the recursion, but also that this time around we get to use the proof, which is a good sign that something is happening.